The first string sorting algorithm that we're going to look at is actually the basis for several more complicated algorithms. It's called key index counting, and it's very useful in a particular special situation. But let's take a quick review of where we left off with sorting. We considered a number of sorting algorithms, starting with insertion sort, and then merge sort, quicksort, and heap sort. And we got to the point where we could find an algorithm that's heap sort that guarantees to sort n items in time proportional to n log n without using any extra space. Unfortunately, not stable. And all these algorithms were useful, or are useful, for any type of generic key as long as it implements the compare to operation. And not only that, we prove that any algorithm that just uses compares has to use number compares proportional to n log base 2n. So in a very important sense, merge sort or heap sort, for example, are optimal. You can't use asymptotically fewer compares for either one, and with heap sort you can't use less extra space. So why do we consider other sorting algorithms? There's a lower bound. Why are we thinking about this? The question is, can we do better? And obviously we're here because the answer is that we can do better if we don't depend on compares. The lower bound, the one assumption made by the lower bound is that we use compares, but we don't always need to use compares. And so let's look at an example. Key index counting is a fine example of that, and it's representative of a fairly common situation where in sorting application, where it happens to be that the keys that we're using to sort are small integers. So in this case, this is supposed to mimic an application where there's students and they're assigned to sections. There's not too many sections, and we want to get the thing sorted. We want to distribute the students by section, and so we want to sort according to the section number, and that's a small integer. And the implication of knowing that the key is a small integer is that we can use the key as an array index then. By knowing that the key is an array index, we can arrange for fast sort. So lots of applications for that. When maybe you have phone numbers, you can sort by area code, or if you have a string you just want to sort by the first letter, you could do it that way. And actually that idea leads to an efficient sorting algorithm, actually two different ways. Now, don't forget that we're sorting according to a sort key, but usually we're sorting bigger generic items that have other information associated with them. If you were just sorting the small integers, you could just count how many ones there are, how many twos there are, and like that, and then in one pass, and then if there's 3 ones, just output 3 ones, and so forth. But the complication is that we have to carry the associated information along, so we have to work a bit harder than that. Here's the code for this method called key index counting, and let's look at a demo. So here's the key index counting demo. Now, to make this a little less confusing and not so many numbers, we're going to use lowercase a for 0, b for 1, c for 2, and like that. So it's the a minus first letter of the alphabet, however you want to think of it. And we're only going to look at 6. So we're supposing that we're sorting this array that has 6 different small integers, and we're using lowercase letters to represent the integers so that we can easily distinguish between the keys and the indices. So now let's look at the processing for this. So the first thing that we do is we go through and we count the frequency of occurrence of each letter. So the way that we do that is we keep an array. Now, the array is actually got to be one bigger than the number of different keys that we have and the number of different small integers that we have. So in this case, array of size 7. And just to make the code a little cleaner, we keep the number of A's in count of 1, the number of B's in count of 2, and so forth. And so once we've set up that's what we want to do, then it's trivial to go ahead and count the frequencies. We simply go through, for I from 0 to n, we go through our input, and when we, A of I, when we access a value in our input, it's a small integer, so it's 0, 1, 2, 3, 4, or 5, and we simply add 1 to that integer and use it to index into the array. So when we see an A that's 0, then we're incrementing count of 1, and we see a B that's 1, we're incrementing count of 2, and so forth. So in this case, we increment count corresponding to D, and then A and C, and like that. So every time we encounter a new key, we simply increment one of these counters. In one pass through, we get an array that gives us the number of A's, B's, C's, D's, E's, and F's. That's the first pass of key index counting. Count the frequencies of each letter using the key as an index. Now the next step is called computing cumulates, and that's a really easy thing as well. All we do is we go through the count array and simply at each step we add the current one to the sum computed so far. So if we look before, we had 2 A's and 3 B's. So that means there's 5 letters less than C. That's the A's and the B's. And there's 6 letters less than D and 8 letters less than E, and so forth. And that's just obtained by, we start with 2, add 3 to it to get 5, add 1 to it to get 6. And with that one pass through the count array, then we can find out, for example, there's 6 keys less than D and 8 keys less than E. And those cumulates tell us where the D's go in the output. There's 6 keys less than D and 8 keys less than E, so the D's have to go in A6 and A7. So this is an array of indices that is going to tell us how to distribute the keys in the output. So that's the next step, is access the cumulates using the key as an index to move items. So let's take a look at, so now remember when we see an A, we're just going to count that as 0, so we're going to go to count 0, and that'll access this entry in the count array. So we go through the whole array to be sorted, and we move each key exactly to where it has to go, and we'll do that one at a time now. So when I is 0, we're looking at the D. The count array corresponding to D has 6, so it says just put D in there and increment that. It means if you get another D, it's going to go into 7. And these things, the way we pre-computed them, are not going to run into one another. So now A, we go, that goes in 0, and we increment the count array corresponding to A. Next thing is C, and so that's going to, it says to put it in 5, and then increment the count array corresponding to C. And F, it says put it in 9. Next is B, we put in 2. Sorry, another F we put in 10. Next is B that we put in 2. So you can see the keys from the input are getting distributed in the output according to the counts and the cumulates that we pre-computed. So now we get the other D, which goes into 7. We get the another B, which goes into 3, and then increment to 4 for where the next one goes. F goes into 11. The last B goes into 4, the E goes into 8, and the second A goes into 1. So that's move the items, again, simply by using the key as index into the count array. And then the last step is to just copy the sorted array back into the original input. That's a demo of key index counting. Quick summary of key index counting. We make one pass through the array to count frequencies of each letter using the key as an index. Then we go through that count array to compute cumulates just by adding each new one into the running sum. Then we use those cumulates and access that using key as index to actually move items over and get them in sorted order, and then move back into the original array. What's the running time of this algorithm? Well, the analysis is actually quite simple because it's just a couple of loops through the array to be sorted and through the count array. And the key fact to note that it takes time proportional to n plus r and space proportional to n plus r. Now r, remember, is our radix. That's the number of different character values. So for ASCII, maybe that's 256, and for genomic data, maybe it's 4. And n, we're assuming we're sorting huge files. So really, this is linear time in many practical situations. There's also the question of, is it stable? Yeah, it's actually stable because when we do the move, we move things with equal keys in the order that we see them. We keep them in the order that we see them. That's just the way the method works. So we have for this special situation, we have a linear time stable sorting method which beats the n log n bound and is useful in many practical situations.